So as we take a look at some different things involving regression and inference, one of the first things we're going to look at here is constructing a confidence interval for the slope. So when we're talking about a confidence interval, the general formula for a confidence interval here, we have the statistic plus or minus the critical value times the standard deviation of the statistic. So here we're looking at the critical value being the slope of the regression line plus or minus the t star score, which is going to have n minus 2 degrees of freedom, times the standard error of the slope. So when we're looking at the formula here, the standard error for the slope, remember we talked about this from the previous lesson, that's the standard deviation of the residuals divided by the sample standard deviation times the sample size minus 1, and the t star score is the critical value with a t distribution where the degrees of freedom is n minus 2. So some different things that we've talked about in the past with t star is very similar to this, except instead of the degrees of freedom being n minus 1, now when we're talking about the slope of a regression line, the degrees of freedom would be n minus 2. So there's two different ways that we go about computing the t-interval for the slope of a least squares regression line. One of which is by using this formula. So there are some different problems, and you'll see in this first example here where we use a computer output table and we basically just take the values and plug those numbers into the formula for these variables to get what the confidence interval is. Another type of problem that we do is when we actually have the data values from the scatter plot and we can put those in the calculator and go about computing the confidence interval that way. So here's an example, and it says earlier we used Minitab to perform a least squares regression analysis on the helicopter data for Miss Barrett's class. Recall that the data came from dropping 70 paper helicopters from various heights and measuring the flight times. We checked conditions for performing the inference earlier, constructed and interpreted a 95% confidence interval for the slope of the population regression line. So remember the regression output that we had from the previous lesson that dealt with that particular problem. So here you got the y-intercept of the regression line, here's the slope, and then here's the standard deviation of the residuals, and then we have some other values here that we'll get to talking about in a moment. So the standard error of the slope, which is this value here, this is the standard error of the slope, that's where that comes from the output. So because the conditions are met, we can calculate a t-interval for the slope based on a t-distribution with n minus 2 degrees of freedom. So in this case, if the sample size was 70 paper helicopters, we would use 68 degrees of freedom here. So if we did the inverse t for that, we would get a t-star score that was roughly 2.0. So here, using the formula, the value of b I'm getting from the regression output right here. So that's the 0.0057244 plus or minus t star times the standard error, which I'm getting from here. And when I do that, I get a confidence interval that's roughly 0.005328 to 0.0061280, which in this case means we are 95% confident that the interval from 0.0053208 to 0.0061280 seconds per centimeter captures the slope of the true regression line relating flight time, which is the y variable, and the drop height of the paper helicopters. So that's one type of confidence interval problem where we basically take the regression analysis that we have and we essentially take different values from that analysis and we kind of plug those into the formula for the confidence interval for slope. Another type of problem is when you actually have data values. So notice this problem, it also gives you a regression output. So I'm going to kind of show you sort of both methods that you could follow here for this problem, because it not only gives you the regression analysis, but up top here it also gives you the data values that went with the that go with the scatter plot. So the question says, in Chapter 3, we examined data from a study that investigated why some people don't gain weight even when they overeat. Perhaps fidgeting and other non-exercise activity explains why. Researchers deliberately overfed a random sample of 60 healthy young adults for 8 weeks. They measured fat gain in kilograms and change in energy use in calories from activity other than deliberate exercise for each subject. So here's the data that they have. So the non-exercise activity represents the calories that they burn using with their non-exercise activity, and then how much fat gain they had as a result of that. So here once again is the regression analysis at the bottom. So here is the slope of the regression line, here is the y-intercept for the regression line, here's the standard error of the slope, and then here is the standard deviation of the residuals. So the question says to construct and interpret a 90% confidence interval for the slope of the population regression line. So one of the things, just kind of showing you this in sort of a state plan to conclude type of format. So in the state part, we want to mention what we're estimating and at what confidence level we're going to do, what confidence level we're going to use. So we want to estimate the true slope of the population regression line relating non-exercise change to fat gain at a 90% confidence level. Then in the plan, we want to check conditions. So in this case, we're going to compute a t-interval for the slope. And when the conditions, or the checking the conditions, the first condition we're going to check is linear. So if you take a look at this scatter plot here on the left, you can see that the scatter plot gives you a set of points that appears to be roughly linear. And then also the residual plot shows a random scatter of points. So remember, when you're looking at your residual plot in terms of linear condition, you're looking to see if the residual plot has any sort of curved pattern to it. Then I also kind of just threw the histogram over here on the side, so you can see here that that's roughly symmetric. So we can assume the linear condition there. Independence, individual observations of fat gain should be independent if the study is done properly. So since this was an experiment, we need to assume that they're talking about the subjects in the study having their results being independent of each other. The normal condition, so if you take a look at the histogram on the right here, you can see that that gets you a graph that's roughly symmetric, so we can assume normality there. Equal variance, it's kind of tough to tell because there's really not a lot of points on the graph. So once again, what we're looking at here is we're looking to see, based on the residual plot, which is this graph that's in the middle, we're looking to really see, do the vertical distances from the points that are below the line seem to be roughly the same as the vertical distances of the points that are above the line. So there's nothing too glaring here that would make me believe that that wouldn't necessarily be true. And then the random condition, the subjects in this study were randomly selected to participate. So in terms of the do part of this, I'm going to go right to the formula. So since there were 16 subjects, I'm going to have 14 degrees of freedom for this, which would get me a t-star score of 1.761. So that's based on a 90% confidence level. So the formula that I'm going to use, here is the slope of the line that we get from the regression analysis. Here's the t-star score as well as the standard error. So this comes out to be roughly a confidence interval of 0.004747, negative 0.004747 to negative 0.002136. And I included some screenshots here and here of the some of the different things that you do with this with your calculator, which I'll kind of get to in a moment here. But the conclusion for this is we would say we are 90% confident that the interval from negative 0.004747 to negative 0.002136 kilograms captures the actual slope or true slope or population, the actual slope of the population regression line relating non-exercise change to fat gain for healthy young adults. So just showing you real quick how you could also do this in your calculator. So if you come back to this slide here where it has the actual data values in the scatter plot. So what I'm going to do with this is I'm going to put the non-exercise change in L1. I'm going to put all the fat gains in L2. And when I do that, I got something that basically looks like this. So I got the L1 non-exercise change, L2 I got the fat gains, and then from here I'm going to stat and I'm going to test. And if you use your up arrow key, you'll notice F and G at the bottom here. You have a linear regression t-test and a linear regression t-interval. We'll talk about the linear regression t-test here in a moment, but we're looking at, for right now, the linear regression t-interval. So I'm going to go to G, and then I have the X list in L1, the Y list in L2. Confidence level was a 90%, so I'll put in 0.90 here. And when I calculate this, you'll see that you'll get a variety of different values here, one of which is obviously the confidence interval, but you have B here, which is the slope of the regression line. You have the degrees of freedom. S is the standard deviation of the residuals. A would be the y-intercept. The R and R squared values, so just remember what those are. The R value is the value of the correlation. The R squared value is the coefficient of determination. So just some different things that sort of come up with the linear regression t-interval in your calculator with those. Some things that we did with scatter plots from back in chapter 3. So just coming back into this here. So similar question that we had, and it said in chapter 3 we examined data on the body weights and backpack weights of a group of 8 randomly selected 9th grade students. A least squares regression analysis for this data is shown below. So here is the regression analysis. So we have, once again, here's the y-intercept, here's the slope, here's the standard error for the slope, and what conditions must be met for inference to be appropriate. So we had the conditions first, the linear conditions. So the scatter plot must show a linear pattern. The observations must be independent. The residuals need to be approximately normally distributed. Key thing to mention there is the residuals. The residuals must show roughly equal scatter from all the x values, and the observations must be produced by some sort of random sampling or randomized experiment. So those are the conditions that need to be met for the confidence interval. So question 2 says, with such a small sample size, it is difficult to check several of the conditions for regression inference. Assume that the conditions for this are met. Construct and interpret a 95% confidence interval for the slope of the regression line. So since there's 8 observations here, n minus 2 degrees of freedom, so there would be 6 degrees of freedom here for the 95% confidence interval, which gets a t-star score of 2.447. So this means that the confidence interval would be 0.0908 plus or minus the t-star 2.447 times the standard error, which is 0.02831. And once again, I'm getting this value here and this value here simply from the regression analysis table, which gives you a confidence interval of 0.02153 to 0.16007, which means in this case that we are 95% confident that the interval from 0.02153 to 0.16007 captures the true slope of the population regression line. You got to make sure you include both of those words in there in your interpretation, relating pack weight, which is the y variable, and body weight, which is the x variable, among these 9th grade students. So that's just some different things involving the slope and confidence intervals. The other thing we're going to look at is the slope and significance test. So when conditions for inference are met, which is the same conditions that we had for a confidence interval, we can use the slope of the sample regression line to construct a confidence interval for the slope B of the population regression line. We can also perform a significance test to determine whether a specified value of B is plausible. The null hypothesis has the general form B equals the hypothesized value. So one thing just to note about this, the null hypothesis, and that's always going to be that the slope is equal to 0. So to do a test to standardize B to get the test statistic, so here's the formula that we use just in general terms to compute a test statistic, but in terms of the more specific to what we're talking about with slope, the test statistic is going to be the slope that you get from your scatter plot minus the null hypothesis value divided by the standard error of the slope. So to find the p-value, we would use n minus 2 degrees of freedom. So here are the details for the t-test for the slope. So remember when we were talking about significance tests, there's essentially the one-sided test, which would be a greater than test or a less than test, and then you also have potentially a two-sided test, which would be a not equal to test. So to give you an example of a significance test involving slope, the question here says, infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Child development researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of the foot caused the infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the children's IQ at age 3 years using the Stanford Binet IQ test. A scatter plot an output table for the data from the random sample of 38 infants is below. So here's the scatter plot on the left. Here's the regression analysis on the right. So just once again, here is the y-intercept of the slope. Here, the y-intercept of the regression equation. Here's the slope. Here's the standard error for the slope. Here's the standard deviation of the residuals. And the question says, does this provide convincing evidence that there is a positive linear relationship between crying counts and IQ in the population for these infants? So just walking you through this in the four-step process. So the state part is we want to mention what the null and alternative hypothesis are. So in this case, we would say that the null hypothesis, and this is the same for every problem that we're looking at when we're talking about regression with slope, is that the population slope would equal 0. In this case, we're going to look at an alternative where beta would be greater than 0. So remember that beta stands for the true slope of the population regression line relating crying count to IQ score. No significance levels given, so we're going to use a 0.05 significance level. So remember, the three things in the state part you want to mention are the null and alternative hypothesis, what the slope represents in the context of the problem, and then what the significance level is. In the plan, we want to mention what kind of test we're going to do. So this would be a t-test for the slope, and then we want to check conditions. So the linear condition, the scatter plot suggests that we have sort of a moderately weak positive linear relationship. The residual plot shows a random scatter of points. So if you notice once again here, the scatter plot doesn't really show a pattern that necessarily looks roughly linear, but it doesn't necessarily look like it's curved either. And if you look at the residual plot, this right here, if this was a relationship that wasn't linear, you would have some kind of curved pattern in your residual plot here. So since that doesn't occur, we can kind of assume that the pattern's linear. For independence, later IQ scores of individual infants should be independent. So due to sampling without replacement, we have to assume that there's at least 380 infants in the population with which they selected those 38 children from. The condition, the normal condition, the normal probability plot, which is this graph over here, the normal probability plot of the residual shows a slight curvature, which suggests that the responses may not be normally distributed about the line at each x value. With such a large sample size, however, the t procedures are robust against departures from normality. So remember, when we're talking about such a large sample size, we're talking about a sample size in this case that would be 30 or more. So even though this is showing a slight curvature because the sample size is large, I'm okay to proceed with the normal condition. Equal variance, the residual plot, which is the plot that's in the middle here, this shows a fairly equal amount of scatter around the horizontal line at y for the x values. And then the random condition, we're told that the 38 infants were in fact randomly selected. So the do part, since I'm okay to proceed with the conditions, I have the test statistic. So in this case, I got the value of the slope from the regression line, 1.4929, minus the null hypothesis, which in this case would be 0, divided by 0.4870. That's the standard error of the slope. So I get a test statistic that's roughly 3.07. So because of that, that gets me a p-value of 0.004. And with this, since we're doing a two-sided test, we would cut the p-value in half, so that would be a p-value of 0.002. So the conclusion with this is that since the p-value is so much smaller than the significance level, we would reject the null hypothesis and conclude that there is a positive linear relationship between intensity of crying and IQ scores for this population of infants. So just finishing up with this sort of similar question here, and this goes back to the problem that we did involving pack weight versus body weight for 9th grade students. And it says, do the data provide convincing evidence of a linear relationship between pack weight and body weight in the population of 9th grade students? Carry out a test at the 5% significance level. So for this, we're going to assume that all conditions for regression have been met, so we can kind of just get right to the math for the test statistic for this. So just kind of jumping right to the do part and the conclusion for this. So the test statistic for this comes out to be roughly about 3.21. So I'm just using my formula there. So we're basically looking at, to do the test statistic, we're basically taking the slope minus 0 divided by the standard error. That's where that That's where that 3.21 comes from, which gets a p-value of roughly 0.018. We're using 6 degrees of freedom there since there was only 8 in the sample. So the conclusion here is since the p-value is less than 0.05, we would reject the null hypothesis and conclude that there is convincing evidence of a linear relationship between body weight and pack weight for these 9th grade students. Would a 99%, question number 2, would a 99% confidence interval for the slope of the regression include 0? Justify your answer. So with this right here, it would, because the 99% confidence interval would contain 0 because the p-value for the two-sided test would be greater than 0.01. So once again, if you're talking about the 99% confidence interval and the 1% that's left over, that's why it would contain that value there. So that's basically the connection that we have between inference and regression equations. So we do some different things with the slope involving confidence intervals. We do some different things with slope involving significance tests. And one of the last things that we're going to look at involving scatter plots has to do with what happens when your scatter plot shows some sort of relationship or some sort of pattern that's not linear, and some of the different things that we can do mathematically to achieve linearity so that we can make we can use some different conditions for inference and make some different predictions using some of the tools that we just spoke of.